Hello, everyone, and welcome to another wonderful day of PChem. So far, we've been building up a conversation about heat and energy that have really been focusing in on internal energy, and thus the only way we can really relate it to heat is under isochoric conditions. And this is a little bit problematic as turns out most of the time the world isn't under isochoric conditions. Instead, we tend to be under isobaric conditions a lot more. A good way to think about this is it might be, say, the difference in between heating a system, say, in a sealed container like a pop can versus in a balloon. So if I heat things um, in a pop can, this is going to be problematic as that pressure will eventually build up and the whole thing ruptures. This is the reason we call bomb calorimetry, because things can go wrong very quickly. Now, under isobaric conditions, it's much more like heating up a balloon. The system will end up expanding, and it turns out that this kind of balloon isobaric analogy is a pretty good comparison to a lot of atmospheric conditions, where I have a system under atmospheric pressure that may end up expanding. And as long as our interactions with the atmosphere are fairly benign, we can treat the system as being close enough to close that we can get a really good comparison. So instead of trying to focus in on isochoric conditions, like a lot of chemical engineers, we as chemists really love ourselves some isobaric conditions. So what we need to do is try and find a better way to look at non-isochoric heat transfer. So let's try and start by getting away from my isochoric nature. And in this case, we develop a general expression for our heat, which is just going to be the change in our internal energy of the system, minus whatever energy is essentially inputted as work. So essentially, if it's not work, any change in internal energy has to be due to heat. Because again, we're assuming a non-reactive system. Now, this only gets us so far unless I know something about W. So our easiest treatment of work was isochoric when it went to 0, but our next easiest treatment is isobaric conditions, where our work is entirely PV. So this means that with pressure being constant, thus isobaric, any work being accomplished is simply due to a change in volume against that pressure. Now, I can go ahead and combine these two equations, have a nice little cancellation of sign, and what I end up with is an isobaric heat. So this is the amount of heat that will be transferred under isobaric conditions, and it will essentially be the change in internal energy plus essentially whatever energy is lost as PV work. So we're essentially just taking that PV work term and adding that back into our energy term as a correction. So this is where we start having a slight problem because heat by definition is a path function, which means it's going to depend on exactly what path my system traversed. So we tend to not like using heat as a variable. But it turns out that isobaric heat is not a path function because it depends on internal energy, a state function, pressure, a state function, and volume, a state function. Woohoo! This means that since there is no path functions on the right side, it means that this function by definition also has to be a state function. So to help keep things straight, we're going to give this new state function a name and call it enthalpy, where enthalpy is pretty much going to be equivalent to heat transferred under isobaric conditions. So we now have a new state variable, which we can essentially use to end up relating the heat under isobaric conditions in this kind of ideal sense, but we also are going to have a comparison to internal energy under isobaric conditions. But one of the things we have to watch out for is that this relationship in between enthalpy and internal energy isn't going to be universal. We have this assumption of isobaric conditions. And it turns out we aren't always going to be able to make that assumption. For example, I may have enthalpy and I want to find internal energy under isochoric conditions. So we need a little bit more of a general relationship. And so our general relationship in between change in enthalpy and change in internal energy will be based on the change in pressure and volume combined together. And so it's possible to essentially separate this combined pressure volume change as P delta V plus V delta P. So this is going to be our more general expression. And you will notice under isobaric conditions, where pressure does not change, this term drops out and we get our earlier expression. So that's always a good double check to make sure that we have. But one of the big advantages is that this is going to allow for calculation of our change in enthalpy, even when I don't have isobaric conditions. So if I do have a change in pressure, I can simply factor this in to my previous equation. So it's again a much more general expression, which comes in handy under select circumstances, which we'll occasionally encounter. And if this relationship doesn't make sense, we can always go ahead and see what it looks like under infinitesimal changes, because it turns out that we like using infinitesimal bases because this is more or less going to show instantaneous change, which is always good, but it also means we can calc the heck out of it. So what we have is a similar relationship that change in enthalpy is related to change in internal energy plus the change in pressure and volume. At which point I just product rule out this change term, and we again get PdV plus VdP. So again, hopefully this makes sense from a mathematical basis as well as a kind of a conceptual basis. Because again, since we have a state function, any change in the enthalpy will be related to the change in internal energy, plus essentially, since I've got a two-dimensional surface, a change in volume and a change in pressure, where these can be thought of as different legs on a path. And being a state function, the exact path I travel doesn't matter, just my beginning and ending points. So this is one of the big advantages of using a state function for enthalpy instead of our more path function of heat. So one of the other important things to make note of is that these expressions entirely focus in on changes of enthalpy. And this is actually probably the more important term simply because just like internal energy, I can't really measure the absolute enthalpy, but it's still going to be useful to have a general expression so we can end up manipulating and do some use it as a mathematical basis for some of our further relationships. And in this case, we do actually see that enthalpy is just going to be related to internal energy, plus essentially the amount of energy stuck in this pressure volume relationship. So essentially, this is going to be largely related to the ability of the system to do work. And it turns out that we can go ahead and express our change in, determine our change in enthalpy using this expression and make sure it matches up with what we saw previously. So again, if I take my calculus terms, what I get is dH equals du plus pdv plus vdp. So again, just by taking the differential of each side, we get our previous expression back, which is absolutely wonderful. But it turns out we also might want to be able to have a more general expression that relates enthalpy to heat in general and not just under the specific conditions of isobaric. So we can do this by taking our expression for internal energy and looking at its dependence on heat and work. So we can essentially just substitute in that expression over here. So now we get a little bit longer of an expression. And unfortunately, it's going to get a little bit longer because while I still don't have a good equation for heat, I do actually have a good equation for work. And it turns out that that good equation is, assuming that we have no electrical work, going to mostly be PV work. And in that case, dW equals negative PdV. Now, do notice that this does not depend on isobaric conditions, because again, what we saw previously is that work equaled negative PdV, and all we had to really worry about was the volume dependence of pressure. In this case, we don't know, and it turns out it won't matter because I have a negative and positive term right next to each other. So these two central terms will cancel out, and I get a reduced expression for enthalpy equals the heat plus the change in heat plus the volume times the change in pressure. And it turns out this expression will become useful fairly frequently. Though again, most of the time we end up focusing in on the isobaric version of this expression, because under isobaric conditions, this last term goes to 0, and I get the simpler dH equals dQ. And so one of the important things to note is that we're going to be seeing here is that obviously enthalpy will have a dependence on the change in pressure. And at least for an ideal gas, we have an idea of the relationship. Enthalpy is going to depend on pressure, essentially linearly related with volume. As we'll see later, this expression will break down a little bit for non-ideal systems. But for now, this actually works fairly well. But what it also shows is that we're going to have a relationship in between enthalpy and temperature, because we've already seen a relationship in between how much I heat the system and the change in temperature of the system. And we've done this for internal energy. So let's go ahead and use our relationship in between enthalpy and internal energy to try and build a parallel between the two expressions. So again, we've seen this so far. Enthalpy is going to be related to internal energy plus PV, but we've also previously shown that the change in internal energy is equal to the change in heat minus PdV, and we just proved that the change in enthalpy is equal to the change in heat plus VdP. So we get these two slightly different expressions for the relationship in between heat and the appropriate energy and enthalpy. And again, one of the big reasons we use internal energy is when we're looking at heat under isobaric or isochoric conditions, because this term drops out. And then under isobaric conditions, the change in heat is equal to the change in enthalpy. So again, choice of what conditions you're working under is largely what drives your choice of metric. Thus, a lot of engineers who are working under in solid state systems where the volume doesn't change really likes internal energy. But chemists, where we tend to work in open atmosphere, much more prefer enthalpy, as it's a more convenient metric. So one of the big advantages of this is that just like we did previously with internal energy, if I go ahead and constrain the conditions I'm operating at, I can essentially make sure that all of my energy change is just due solely to temperature. And so we saw this with internal energy, that my change in internal energy is going to be equal to my change in isochoric heat. And then under this conditions, the only place for that energy to go is into the kinetic movement of my system, which essentially is temperature. And the ratio in between the amount of energy added and the change in temperature was my isochoric heat capacity. Similarly, under isobaric heat capacity, the only place for the energy to go is again into temperature, or more appropriately under this conditions, there's going to be a linear relationship in between the amount of energy heat added and the temperature of the system. And in this case, that coefficient is going to be my isobaric heat capacity. So again, isobaric CP is going to be my isobaric heat capacity. And unlike my isochoric heat capacity, which just essentially included energy that went straight into the change of the molecular speed, whether this is rotations, vibrations, translations, my enthalpy and its isobaric heat capacity is also going to encompass how much energy has to be expended into PV work. So again, we're going to be looking at this a little bit closer next time as we dive in headfirst into isobaric heat capacities. Till then, take care.